Yeah, hi, I'm Pradeep. I welcome you all to the LLVM Social Bangalore. And before going to the talk, I'll just share a few interesting news from LLVM. And so there are a few upcoming events in the LLVM community. So there is this new community.o meetup, which is uh, a community to improve diversity in compilers. And they have been conducting a lot of meetups, especially there is a women in compiler meetup. Uh, so that's been very actively conducted. So if you're interested, please check that out. So yeah, I'll share the slides and the links to the meetup after the meetup is done. And so that is the LLVM Bay Area meetup, which is an in-person meetup. Yeah, this is the first in-person meetup after the lockdown. So uh, I hope anyone in Bay Area, please check this out. So that is the 7th annual workshop on the LLVM compiler infrastructure in HPC. So LLVM is used in almost any software place. So HPC is one of the main use cases of LLVM, and there are a lot of interesting things happening in HPC. So if you want to know anything about that, please check this conferences. And so the highlight is the LLVM developers meeting, which is the annual developers meeting. This is as last year's meeting. This is also happening virtual online, and like the social meetup here, you'll find LLVM developers from all over the world, and it's not just about the technical talks that happen in the meetup. It's about the community and the connections that you make. Since it's virtual, it'll be easy for anyone to join and meet interesting people. So definitely check this out. I think you'll get the registration soon. So I think this year's GSOC is over, and there are a lot of interesting projects, especially in the LVM GSOC projects. I've linked to the project page, and yeah, please check that out. And that is similar to GSOC. We have Outreachy, which is a special version of GSOC. Yeah, we have a couple of projects there. I think there was a blog related to that, and the link is here. So please check that out too. And something from the mailing list. So recently there was a talk about deprecating the legacy pass manager. So in the LLVM, we have two pass managers. One is the legacy pass manager and the new pass manager. So the new pass manager is a rewritten a modern version of the pass manager, and it has lots of options and very user-friendly debug capabilities, and it's been around for a long time. And yeah, I think with LLVM branching out to 14, I think LLVM's the top of tree is version 14. The discussion about deprecating the pass manager has started. And there was another interesting discussion on LLVM ISNAN. So ISNAN is an interesting to check whether the value is NaN or not. And there was a discussion where how to handle optimizations related to ISNAN. For example, for any floating point math operations, so there is a fast math mode where you optimize, fast math. So floating point numbers, you have doubles and floats, and you have precision, ranges for them. And in fast math mode, you don't want a lot of precision. You can, optimize a lot of fast math operations without regard for precision. So, and one of the characteristics of fast math is you don't allow NaN values. So NaN values, could take a bit of um, instructions to handle. So in the isnan mode and the fast math mode, isnan can be optimized away because you don't allow nan values on. You cannot check for a value when you enable a nan value when you enable fast math. So there was a good discussion about isnan intrinsic in yeah, and the link to that is there. And there was another discussion on clamp implementation. So there was a blog that compared Rust implementation of clamp. So clamp is a built-in function in most of the programming languages, and clamp and the blog compared implementations of Clang versus Rust, and Rust was really doing well. And there was a bug filed against LLVM on and why Clang was generating why Clang was generating bad code for clamp, and it was after that it was fixed. So please check that out and see why it was why one of the optimization called SROA, scalar replacement of aggregates, was doing bad. Yeah, there was another interesting discussion about jump threading pass, optimizing DFA, deterministic finite automata code. So which was so one of the benchmark had this. So you can check out the review on how they did it. And there was an interesting explanation about how different register allocators in LLVM work. So there are three different register allocation. One is fast, one is the basic, and the other one is a greedy register allocator. And there was a good explanation of how the register allocator work. Yeah, please check that out. And there was a very interesting a link about how RISC-V vector intrinsic will be implemented in LLVM. So yeah, it's a very long discussion. So RISC-V vector it's a very revolutionary idea, but a vector process has been around for a long time, but RISC-V vector reinvented it, and yeah, I think ARM is also following up with their own scalable vector extension. So please check that out. And not just related to there have been a lot of discussions in LLVM developers forum, and you can check about GPU related news in this link. So there are whenever there is any discussion about GPUs, you can check this out for any updates on the GPU latest stuff in LLVM. And there is also OrcJIT. So Orc is the just-in-time compiler in LLVM, and it has so previously there was LLJIT, and it was upgraded to OrcJIT. OrcJIT is a very modern API, and it supports a lot of interfaces. And Lang Hames from I think he's from Apple or Google. Yeah, he sends out weekly notes on OrcJIT, on updates on OrcJIT. So yeah, please check that out. And apart from the discussions in the mailing list, so I have links to the mailing list towards the end. Apart from that, there are a lot of sync up meetings where so LLVM is not just a single project. It has a lot of sub projects. So we have Clang, MLIR, we have Flang, the Fortran front end, and each community have their own discussion, and I have links to few ones. So MLI open discussion meetings are community meetups. It's like weekly meetup that happens on Thursday, where you can find MLIR interest related topics. Yeah, so there is LLVM loop optimization working group. It's about loop optimization and the current state of loop optimizations, and you can find a lot of interesting discussions related to loop optimizations. And there is a specific LLVM RISC-V sync-up calls, and there are meetups related to memory SSA. So memory SSA is it's like SSA for memory operations, and they have their own sync-up calls, and there is an alias analysis technical call, and there are a lot of technical calls that you can attend to and learn from. You just don't have to, if you don't find anything, useful material related to it, you can just post it in the developer forum, and get your your doubts addressed. So so these are the key links that you want, that you have to know. If you're in LLVM, you just the main mailing list will be LLVM dev. That's where most of the discussion happen, and there are other mailing lists related to sub projects. So LLVM dev is mostly about the happenings in the any discussion related to LLVM, and there are Clang specific sub mailing list. There is MLIR and stuff like that. And there is LLVM Weekly, which I would highly recommend. So LLVM Weekly is a digest of the discussions happening in LLVM Dev and other mailing list. It's prepared by Alex Bradbury. He heads the LLVM risk pricing sync up call. So he puts together the good list of mailing links from the mailing list. So please subscribe to it, and it keeps you updated on what's happening in the LLVM community. Yeah, and there is an LLVM discourse channel, which is like a modern version of the mailing list. And I don't know if they're planning to move to discourse completely, moving away from the mailing list. But yeah, it's a good forum, and I think most of the MLIR discussion happens in the discourse. So yeah, please check that out. And that is the LLVM Discord server. So if you want to have, if you are very active in Discord and if you want to chat with people who are working in LLVM, you can just go there. And there are different channels related to each projects. And we have even India specific channel. So if you want to ask anything specific to India, there is a channel in the LLVM Discord server. Yeah. Think yeah, that's it. So coming back to the talk, so today's talk is about deep learning based compiler optimization, and I welcome Dr. Divendra Das, Senior Principal Engineer, Intel. Yeah. So before the talk, I just give you a brief a biography of the speaker. So Divendra Das is currently a senior principal engineer at Intel Corporation. His interest lies in the enablement of AI in compiler algorithms, and he's also interested in applying machine learning and deep learning algorithms for molecular drug design. So before joining Intel, he headed the compiler team at AMD, where he led the team which developed AOCC, which is AMD's premium optimizing compiler that achieved world record spec bench scores. Early in his career, he spent many years at HP and IBM working on compilers, computer architecture, and program performance understanding. Apart from his industry career, he holds a bachelor's degree in computer science from Jadavpur University, a master's degree from Indian Institute of Science, and a PhD from IIT Kharagpur. So without further ado, I hand over the stage to Dr. Divendra Das. So yes,
Okay,
the stage is yours.
Thank you, guys. Let me share my screen. Is it visible to everyone?
Yes.
Okay. So first of all, thanks to all the organizers from the LLVM Bangalore meetup group, especially Pradeep, who interacted with me quite a bit in getting this going, and also to Aditya and others. So today's talk is kind of a bit of a repeat of the talk that I gave at PACDD. So if you had already looked at it, maybe you will see lots of similarities. But what I wanted to do was, even if you have heard me there, maybe this will be the opportunity for you to ask any questions, stop me, and have some discussion. So this is a very, very, I'll say, emerging topic. Most of the, either research compilers, if you see open source compilers, or compilers which are proprietary, they do not have much of deep learning. Maybe they have some preliminary machine learning based stuff, but not much of deep learning based compiler optimization. So in a way, what I'm talking about today is probably something people will get more involved in and start working in the coming months and years. So there have been some work in the last few years. So what I'm planning to do is give a very high level overview of some of the important work. touching various aspects of the compiler, and then give you a list of kind of reading materials and things like that, which you can look up, and then maybe in some future meetups we can have more discussions around that. So also one of our work on peephole optimization using machine learning is probably going to come up in LLVM HPC, where it will be a lightning talk. And you'll probably hear more about it later if we can get it to a slightly more major conference or to LLVM Dev or things like that. So yeah, so let's start. So by the way, my work at Intel is slightly orthogonal to what I'm going to talk about here. So in my work at Intel, I mainly work around an LLVM-based compiler for the deep learning software stack for the Habana accelerator, where the accelerators are meant both for training and inference. So there, I mainly look at machine learning models and then try to optimize the kernels, how to do fusion, how to do partitioning between various kernels, how to pipeline them, etc., etc. But in this work, it's slightly different. This is more like, how do you modernize or do machine learned optimizations in the compiler itself, not develop a compiler for a machine learning stack. Okay, though it can be used in that sense also. So I'll give a brief background. I know the brief background for you folks, because you all come from the compiler community, maybe not very important, but I'll still go through them. And then I'll talk about four important, or let's say I'll not say important, but four different techniques that have been used to optimize or do some amount of code understanding through a machine learned framework in the compiler. The first one is DeepTune. This is the work from Chris Cummins, who did this work at University of Edinburgh. Chris is now at Facebook AI Research, working on a kind of a compiler gym similar to a Facebook AI gym, which is for reinforcement learning stuff. So DeepTune won, I think, a Best Ever award in, I think, PAC 2017, and it's on the first work to look at end-to-end deep learning of optimization heuristics. The next one is from MIT, Charit Mendes and Saman Amarsingh's team called Ithamal. This mainly looks at how to predict throughputs or kind of performance of hardware for each basic block of assembly instructions that you have. Then we have our work based on graph coloring, and which uses LSTMs to do graph coloring based register allocation. And again, Charit and Saman Amarsingh's work on compiler auto vectorization using imitation learning. So these are four. These are not the only ones, but this will give you a fair idea. There is another set of work which I initially thought of talking about, but then the talk becomes really long. Probably, or maybe we can ask the author himself to talk about it in a future meeting. This is a work from IIT Hyderabad by the group there working on the LLVM compilers. And so they have worked on representations of LLVM IR so that it is more amenable to machine learning and things like that. So that I'm not going to talk about. That's itself interesting and will take up a long period of time. And then I'll do some, what are the things that we can look at in the future. And it's actually a very, very interesting area, and it requires a lot of people to really look at the problem in depth from the machine learning aspect or a machine learned aspect to see how we can, whether we can modernize our optimizations, whether you can, do as much of learning from the data, but still probably have human in the loop in some form. Okay, so stop me if you have questions. We can have short discussions and then we can proceed. So as all of you know, the compiler optimization framework consists of a large number of passes, and usually what happens is that you do an analysis and then you do a transformation, you do analysis, you do a transformation. And this kind of proceeds for some amount of time. And once you have a fair amount of analysis and transformation, you finally do your optimized code generation. So this is a very high level view of a compiler optimization pass. And lots of compiler optimization, if not all, depend on carefully constructed heuristics. So if you are a compiler engineer, most of the times what you have been doing is looking and tuning at these, looking at these heuristics and tuning them. And some of these heuristics have been there for tens and 20s of years, many years, maybe popularized by older compilers, and they have been found to be very effective and continues to this day. But there are still many open questions. One is obviously a very well-known problem called the phase ordering problem, like which optimization order to apply. And there have been a lot of work in the past using traditional machine learning, using like genetic algorithms, blah. And then now people are trying to do this using some kind of reinforcement learning as to figure out which is the best optimization order to apply. And it may be actually be different for different code. And today it's just static for us. Like at O2 and O3, if you look at your pass managers, you'll see that you'll have one pass after another defined statically, and then, or maybe based on some flags, some optimizations may be called or not called, but then it's not that the optimizations are not called or called based on the structure of your inputs or other things. Then open questions like, when you do complex optimizations like inlining, you have to answer the question that which function should be inlined so that you get good performance but don't get a lot of code bloat. And this is also once again a very complicated problem. And scheduling and register allocation. Some people have combined these two in earlier work to present a single optimization based on both using some kind of an optimization, let's say a kind of a optimization framework. But in general, if you see, I think in the LLVM compiler, you will have a single register allocation pass and two scheduling passes, one before the register allocation and one after, because as you know that once you do register allocation, your schedules may change because of the lifetime of the registers. Then questions like, which loop should you unroll, how much you should unroll the loops. Once again, if you look at the loop unrolling infrastructure in LLVM, lots and lots of heuristics on how will the code be like once you unroll. So LLVM is trying to kind of guess that as a result of the loop unrolling, how much advantage are you going to get? Will you get dead code elimination? Will you get common sub-expression and all these things? So as you can see, we're kind of trying to predict how it will behave going forward. And many of these things, many people in the compiler community already understand and know that would probably be useful to move to a machine learned phase. Now, not necessarily fully machine learned, but at least have some amount of machine learning starting point for some of these optimizations. However, if you look at, once again, if you look at LLVM, if you look at GCC, if you look at most of the other commercial compilers, there's hardly any machine learned phase that exists today. Maybe a bit here and there, but not much. Also, as you can understand, you are compiler developers yourself, that maintaining these heuristics is not always a scalable problem, especially if you're working for a hardware company, which most of you would be in many cases. And the hardwares are coming in at a fast clip, let's say once every year or once every 1.5 years, which is really, even in AMD or Intel, that's kind of the cadence that they're trying to maintain for their various hardware. It is difficult to tune and modify and rewrite these heuristics for this new hardware in such a short period. Now, people may think 1 year is a lot of time, and if you have a 10-20 member compiler team, that should be doable, but that's not the case, because literally you have tens and hundreds sometimes of software optimization passes in the compiler which you may need to tune or adapt. So people may put in fragile heuristics which may work for one hardware but may not work for the other hardware. and things like that. And the space of possible optimizations is so vast that, writing test cases or developing infrastructure to test all possible combinations of inputs while you are developing these compiler optimizations are very, very difficult. So this is the background in mind. And as I said, it's not that deep learning, machine learning, whatever you call it, is new. People have already thought about it. People have thought about how to apply it, but it has not really taken off. There have been earlier techniques. So I'll suggest this very good kind of a review paper by Wang and Boyle called Machine Learning and Compiler Optimization. This really doesn't touch upon some of the work I'm going to talk today. I think it was published in late 2018, early 2019, some time frame. So it is still mainly, let's say, traditional machine learning optimizations, but still it gives you a very nice overview of where the traditional compiler writers have at least tried or thought about using machine learning in the compiler optimization phase. Now, as you know, most of the compiler writers, what they would like to do, they would like to know, just give me a minute, please. Yeah, the room is getting a bit dark. I can put up the lights. Okay, so given a program, compiler writers would like to know, what kind of optimization do I need to do to execute them faster, have smaller code footprint, reduce power? And as I said, the search space is so huge that it's not possible to get or gauge the effect of all of these things on the compiler writer. So what did the early work concentrate on? So if you look at, let me try to get a pointer. Okay, so the early work on trying to use machine learning for compiler optimizations used what we know in the machine learning community as feature engineering, right? So what does feature engineering mean? Feature engineering means you take, for example, you have a loop and which you want to optimize for something, let's say unrolling or caching or whatever it is, and then you have a control flow graph or even just maybe take the loop body in its IR form as in LLVM in some form, and then you try to get some important, what you think or what the compiler writer thinks based on experience are important features of those loops. Say, for example, how many number of instructions in the loop, how many load instructions, how many store, are there branches, what's the probable cache miss rate for this loop if you are using a lot of memory bound accesses. And then once you kind of come to a good number of features, maybe 10, maybe 20, maybe 30, 50, whatever may be the good number of features, you represent, let's say, some of most of your regions of code using this kind of features, which you collect by looking at the program either statically or by also collecting some dynamic data. And then once you do that, you train your programs with a machine learned model using all these inputs for whatever specific optimization you have in mind. For example, loop unrolling. I want to know for each loop how much I should unroll it by. And what you can do, let's say in an older compiler, is you can get features for each of these loops, let's say some 10 features for each of these loop. And then you kind of run your programs with the loops unrolled with different unrolling factors like 2, 4, 6, 8, 10, 12. I mean, obviously you'll take a lot of time trying to do that. And if you look for a big program, if you have, let's say, 200 loops, the number of combinations of each one is a huge one. So just creating the training set itself is maybe a problematic one. But let's say you have one. You have a good training set, which says that, let's say, if not the best, but probably a good unrolling factor for this loop is 6 or 8 or 4. And so you train using this, what is called as a supervised learning model. And you train whatever, neural net, decision trees, any of these older, mechanisms, and you get a model out of it. And then when you are given a new program or let's say a new loop, you can say, okay, given that I've seen so many of these kind of loops earlier or similar loops earlier, looks like the unrolling factor will be so and so based on my model, and it predicts something. Okay. And it's a good thing because you can learn not only from actually learning the program, but you can even take training set from learning running GCC or ICC or some other good compiler and see for these loops with certain characteristics what is your loop unrolling factor. And then you can train and then predict. So, you can actually have a decent performance out of it. It's just not bad. And as you can see, you can probably do away with most of the complex heuristics that a compiler will have. It will look at various things. It will try to predict how much optimization will happen and so on and so forth, which probably you can do away with. You just need to have the model and then you predict. Now, it can so happen that model does well with certain kinds of code, doesn't do so well with other kinds of code. And so you may need to upgrade your training set every now and then to create a better model incrementally, as you go further. So this was like the old technique. The new technique is not very different in terms of the flow, that you may still need to capture something, build and train and then infer. But what has happened over the years is with the deep learning stuff, as let's say, all of you would have come across all these various image processing models and other stuff, that people have kind of stopped doing what is called quote unquote feature engineering. That is, I really don't want to extract features because I really don't know which are the important ones. Maybe I'm missing something important. Let's say maybe something like, number of semicolons are important. I'm not saying just as a joke, but maybe the number of semicolons are important. I didn't look at it. So instead of trying to do feature engineering, the trend now is to push your entire code. It may be the full for loop or full function or maybe a full graph, whatever it is, whatever form you are representing your program. Push the whole thing. And then you build a model and let it learn from the input set. Whatever the features are, you need not know. It will be all embedded in your neural net. And then you try to build a model which is as close to your training set as possible, and then you try to infer for your program. So this is actually the trend. So before I start looking at some of the important ones, any big question at this point?
And Didi, this is Venkat. My question is that are there, the most of these machine learning techniques tries to replace some of the heuristics compilers trying to take, right? Are there trends now where is it trying to replace any such optimization in terms of correctness? I'm asking. So is it always whatever we have seen is trying to replace heuristics? Is now machine learning is going to replace a complete optimization in terms of correctness and other things?
Yeah, so if you look at it, let's say if you look at one of the recent papers from Google called MLGo, where they are doing the entire inlining, though it is for code size reduction, but they are doing the entire inlining through the reinforcement learning technique. And there you can do both the correctness as well as the optimization. But you raise a good question, because if you look at most of the machine learning models, deep learning models, many of these are things like quote unquote predicted with a high probability. Let's say, you have an NLP system where you have a sentence and you are predicting the next few words or the next sentence. So there the prediction happens with, let's say, I think the next word will be so and so with a prediction of 0.9 or 0.8. Now, then they are rated, and then usually you pick the one with the highest prediction. Now, in general, many cases it may be wrong, but okay, it doesn't really cause much of a disturbance. But with compiler, that is not the case. That's why it's a very good question, because the compiler, if you are predicting something wrong, even with high probability, then you are as good as gone. So that will still is a bit of an open problem, that in cases where correctness needs to be guaranteed, like you will see in the work that we did with register allocation, what needs to be done? I mean, do we need to run some special stuff at the end? Do we need to do something more to ensure correctness? So I think it's still a bit of an open problem where we have to ensure the correctness. And I personally think that we may need to do something outside the model, because many of these models may not ensure the correctness of your code. But if you go towards reinforcement learning, in most of the cases, you may be able to put some kind of restrictions in your reinforcement learning. As you may know, reinforcement learning is a expansion of your search space technique, and you can stop the illegal paths from being taken by encoding your constraints there. But it's a good question, and I think that part is slightly open. You will see, in our work, we have actually tried to do some people using some of the DL techniques in the LLVM HPC paper coming up, and we try to address some of the correctness concern there as to how we can do it. But yeah, good question. I think that's still one of the slightly more open issues that will be there when it comes to compilers.
Thanks, Didi. So I understand now it's all a mixed model. So you do something outside of your model to ensure the correctness.
That's what it looks like. But with reinforcement learning techniques, I think many cases can be handled in the reinforcement learning space. But whether everything can be, ensured, I'm not very sure, because we have really not seen, let's say, something like dependent analysis being done through a deep learning technique, and then everything is being proved to be correct. So we haven't seen that kind of work yet.
Thanks, Didi.
So we'll talk about four different optimization. I'll not say optimization per se. Let's say four different techniques of how some of these things are getting applied. As I said, I'm not going to go deep into, or at least give a very deep view of how you will be representing your programs. That itself is a challenging topic. There are many ways to do that. And maybe we should be asking one of the experts, like Professor in IIT Hyderabad, to come and give a talk. And Ramakrishna from IIT Hyderabad, they and their students have done some work around that. Yeah. So let's go without much further ado into some of these techniques. So first one is Deep Tune, which is end-to-end deep learning of optimization heuristics. As I said, this was done by Chris Cummins and team. And let me tell you what let me tell you what the original problem is. The problem that Chris and his team tried to attack was, given a piece of OpenCL code, and many of you know OpenCL is used to code programs for your GPUs. So if you have a piece of OpenCL code, the question was, does this OpenCL code run better on the CPU, on the GPU, or maybe it actually runs better on the CPU because of various constraints of GPUs, right? People may know that GPUs don't handle a lot of control flow very well, because it needs to stop certain number of threads before it can start the other threads, etc., because of how the GPUs are designed. So he took a lot of OpenCL code and tried to figure out, like, can I predict that this OpenCL code actually will run better on the GPU, or maybe it's just better to run on the CPU. And how do you do that? So he didn't do that by using any feature engineering or anything like that. So this is the overall view he took. So he took the OpenCL code, basically a kernel from the OpenCL code, used some source rewriting techniques so that you can have kind of a normalized version of the OpenCL code for all kernels. And then you use something called an encoding, so that the deep learning model can understand what this code is like. And once you do the encoding, there is also a phase called embedding, which is mainly embedding your encoded sequence in a kind of a vector space. If you're aware of techniques like word-to-vec in the natural language processing domain for deep learning, you would know what it is. And then you go through some long short-term memory. So I'll not go through details of this particular deep learning techniques. You can look them up, but LSTM can be thought of as, if you are not familiar, LSTM can be thought of as a neural net with a kind of a time dependency. Okay, it's a kind of a chain, and then you get an answer. You get the input, and you get the answer at the end of the chain. And so the LSTM takes your entire encoded and embedded source input into the chain, and then outputs some sequence, and then you get some auxiliary inputs, like this is mainly about your hardware in terms of your GPUs or CPUs, and then you do some batch normalization, and then some dense optimizations, dense operations like matrix multiplies, and then you get your predicted device mapping as to whether it should go to the CPU or the GPU. And this is like, the overall things in much more detail. So for example, the input is your kernel, right? So it can be a kernel like this. It's called the memset kernel. It takes your normal stuff as in OpenCL and, just setting some values. And then what does the source rewriting do? Source rewriting is just a normalization technique because if you see the names of the function, the variables, except your library calls, right? They really don't carry much of meaning. So these are all normalized. Like for example, the name is always called A and then capital A, and then your parameters are called small a, b, c, and then your local variables also start from small d and things like that. So once you normalize it, what happens is kernels which have a similar structure will look similar in this normalized form, right? Even if you call memset kernel 1, memset kernel 2, it doesn't really matter. You'll all get similar results. Mm-hmm. And then you have a source encoding. Source encoding is nothing else but giving an ID number to each of the tokens that you have in your in this set. For example, kernel gets a token, space gets a token, void gets a token, your capital letters get tokens, your brackets, etc. So this is just a kind of getting an index. And then you create this index. For example, once you tokenize this whole thing, tokenize an index in the indexization of the whole thing, you will get something like this. For example, you'll get this 01, 02, 03, 02, 04 based on, if you look at this, like underscore kernel gets you 01, space gets you a 02, void gets you a 03, and so on, and you get this sequence, right? This is actually a long sequence. We have just showed you in terms of rows and columns, but it is actually a long sequence. And at the end, there is a pad value in the sense that, not all of your kernels are of the same size. In general, will only support kernels up to certain sizes because your LSTMs will be of finite sizes and things like that. But these can all be taken care of. And then you do the embedding and you'll do the LSTM, and that's how things will come out. So I'll show you in the next part what the code sequences actually look like if you have already programmed using TensorFlow and Keras. You will be familiar with this kind of structures, right? So forget about this part for the time being. You will, if you see your input model, right? It will have your code, and then this is basically your already your indexed code, right? In this, and then from there you convert it to an embedded representation. And when I say converts from sparse to dense representations, it just means that your indices can be a large number based on the vocabulary of your tokens, right? Let's say, I don't remember the exact number. It runs into several hundreds for OpenCL that Chris developed. And then this gets into an embedded dimension of 64. That is, you kind of compress this sparse representation to a dense embedding of 64 vector size, so that your similar values are represented close to each other in the vector space. And then you apply your LSTM. There is a 2-layer LSTM, and then you get your dense outputs from this 2-layer LSTM and with a sigmoid. And then you concatenate it with your auxiliary input, which is mainly for GPUs, your work group size, and data size for CPUs is something else. You do a batch norm and you do again some dense, and finally you will get an output in terms of your, when you say categorical cost and with the loss, and you'll get your output in terms of a 0, 1 value, which says that 0 is for, map it to the CPU, 1 is map it to the GPU. And this is your total code that is going to be running, and this is the training code that will run. And once you have trained your model, you can use the model. So once the model is trained, you can store the model, and then you can use that model to predict. Okay, for the entire. So this is like, if you look at it once again, for this entire input for the entire input, like you get your OpenCL code, and after going through the entire model, you will get your CPU or GPU mapping without doing any feature engineering specifically saying, okay, this is my loop, do this is the number of instructions, load, store, blah, 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 nothing, right? You are just representing the whole kernel as is, whether it has many loops, if structures, whatever structures they are there. You maintain that structure, create an indexization out of it, embed it in a 64-way vector, then pass it through. So this is the body, this is the main body of your, this part you can see is the main body of your model. Couple of layers of LSTM and batch, norm, and dense, and you get final prediction for your CPU and GPU, okay? And you can actually see the entire Python code here in this link. You can actually download and even run it in Google Colab or any of these things. And you should be able to
Can you
run
go
it.
back to your previous slide? The one which was showing various phases of deep tune. Yeah, so if you replace the first two stages can also be performed for a regular C++ function, right? If we generate a sequence encoding, a regular application can also,
yeah.
So complete application can be partitioned about which heterogeneous hardware should it go on, which function.
Yes.
Yeah, it's a generic thing. Okay, thank you.
Yeah, the only thing that will have is C++ and others, your number of library calls and options may increase. So what will happen is each of them will have a different vocabulary. In OpenCL, C code may have a slightly less vocabulary than the general C++, but you have to see. Maybe the vocabulary will be slightly different, and you may need to tune your embedding dimensions and things like that. Otherwise, yeah, theoretically it can be applied.
Okay.
So this is, I'll just show you some performance data, but before that, we don't need to go through everything, but this is a kind of visualization of the deep tune. And if you look at the visualization of deep tune, very interestingly, once you take the kernel, do the source rewriting in its normalized form and do the encoded sequence, and then do the embedding, you'll see that things like let's say variables are embedded close to each other in the embedded dimension, which actually means that variables have similar properties. That's what it means. And then you can apply various heuristic models based on obviously your hardware. As you said, because of the auxiliary inputs, your hardwares will give you different kind of characteristics, and then finally based on that, just forget about this CF:1 and 2 and stuff like that. You'll get different kinds of predictions based on that hardware. But the interesting part is once you embed and you see the embedding, you should be able to see, like, for example, let's say for and while, right? These two keywords should come close to each other in your embedded sequence because these two behave similarly, all right? Or things like single dimensional, multi-dimensional arrays should be close to each other. So that kind of stuff. So what it literally means is the embeddings will show you that these tokens or these things in your source language are behaving similarly, and once that happens, you can then use your deep learning framework to do the rest of the stuff. And this is very similar to word2vec. And if you guys know about word2vec, you should be able to understand very well. But if not, just try to look up what happens in word2vec. For example, in word2vec, the vector. So this is actually work that was done in Google. So what they did was they looked at the entire wiki corpus and other things and tried to give a 300-dimensional embedding to each word. And so they're like, if you look at king and queen, they are very close to each other because both of them mean kind of royalty, but they have a difference because one person is a male, the other person is a female. Okay, so that's how. And king and queen will be pretty far from, let's say, a car or a horse, okay, or an airplane. So that's the word2vec. And you use the word2vec because if you have a sparse representation, the models of machine learning have a tougher time learning the final outcome. But once you make it dense, let's say 300-dimensional embedding or 100-dimensional embedding or 200-dimensional embedding, whatever you do, it becomes a much more compact representation, and then the models can learn your inputs and outputs much better and much faster. And so this is some kind of performance that Chris and others showed. So what they showed is there are already older techniques for doing similar stuff, which also tried to do a mapping for CPUs and GPUs. And there's something called optimal static mapping. It is nothing else but just look at the kernel and figure out. Most of the times running on the GPU will give you better. So it's almost like a kind of understanding a bit of, let's say I see that if there are more of control flow, I'll go to the CPU. So that kind of a mapping is a static mapping which achieves about 58% accuracy. And there was a previous paper, I think about 2-3 years before Chris and others published, which actually had those kind of feature engineering done using handcrafted features and some kind of, I think, decision tree machine learning, which achieved a 73% accuracy for prediction. And then, Chris and others predicted that they could achieve accuracy of about 84%. And both across, two different kinds of GPU. Now, later, as I said, Professor Ramakrishna and their team used a much better representation. So instead of doing this kind of embedding, they took the LLVM IR. So let's say as someone was asking C, so let's say it's from C++, they took the LLVM IR and they did an actual vector representation in 200 dimensions or 200, a 200 dimension vector representation of the LLVM IR. It's an interesting paper called IR2Vec. You can look it up. And then once they use that, they get much better accuracy than DeepTune. I think they get at least close to 90 or more than 90% accuracy with DeepTune. So as you can already see that how you represent your program in intermediate form or whatever form, how do you do your embedding, and some of this kind of stuff can have an impact on your model and the accuracy of your model. And this is still an ongoing research. There have been several pieces of work. IR2Vec is one of them. There's another work called Code2Vec, which came from, I think, one of the Israeli universities. And then there is a work called Inst2Vec, which came from Tal Ben-Nun and others from ETH Zurich, where they actually look at some kind of graph representations of the IR2Vec, basically the CFG representation. So these all have different kind of accuracies. And then when you are trying to model your C++ or Java or Python, whatever code you want for your optimization, this is one thing you need to think about a lot as to what will be my intermediate representation and how will I represent the representation input in a way to the model so that the model can learn better or learn faster. And this, as I said, still is a kind of openish problem. There have been some solutions that have been given, but we probably haven't heard the last of it in terms of how to represent all of these. Okay, so that is the first one. And the next one I'll go to talk about is called Ithamal. Ithamal came from Charit and his guide, Professor Saman Amarasinghe in MIT. And what does Ithamal try to do? So from an end-to-end optimization, which we saw just now in DeepTune, we go to a much more constrained problem. And what is the constraint problem? And this, many of you have worked in not just the middle end of the optimizer, but have worked in the back end of the optimizer and have analyzed a lot of assembly instructions, would have realized that sometimes you are unsure that whether this assembly instruction actually will perform better. Now, usually what it will do is you will produce it, actually run it, you'll see how it performs, or maybe use some kind of a simulator or things like that and figure out how it will perform. But in many cases, what happens is you will need to have tools which will be required to give you estimates of these in terms of clock cycles without actually, running them. Because, if you have to run them always, sometimes it's even if you run them, you are always not sure of, what is going on in terms of the fact that, you really have not been able to model all your stuff well and things like that. So people have built analytical models. Like if you are aware LLVM MCA, you can use that. Usually a lot of people use it once you get a basic block of instructions. You can use LLVM MCA to kind of figure out what will be your cycles. Now LLVM MCA takes data from your, scheduling and instruction TD files and all that and tries to give you an estimate. Similarly, Intel internally has a tool very similar to LLVM MCA, which actually precedes LLVM MCA called ISCA, Intel Architecture Code Analyzer. And what has been found is, though these are all good tools, modeling the microarchitecture of a complex hardware is not easy, right? So for example, here you can see block diagram of Cascade Lake, which is our previous gen CPU before Ice Lake. And it has a lot of complexity. So even though, microarchitects sit with simulation engineers and recreate this, it's very easy to omit details. People have figured out that sometimes specs are not accurate. Sometimes some details are proprietary and are not known to the, external researchers or implementers because it's not really an open source hardware. So all these things make accurate modeling of processor complex. And as I said earlier, that always running it really and figuring out whether it is better or not is not an option, because in the compiler, you may need to decide between code generation of X versus Y and or various other techniques, and you may want to figure out how many cycles it will consume before actually running it. So once again, so what does Ethamal do? Ethamal uses, as you can now well understand, the drift of this kind of work, that Ethamal will try to replace your model with the learned neural network, right? So instead of using an actual model, what Ethamal has tried to do is it has captured 1.4 million basic blocks from Spec 2006, Spec 2017, NAS benchmarks. And what it has done is it has actually run them through your actual hardware, let's say Cascade Lake or AMD hardware. It's not actually, doesn't show any results on AMD hardware, but you can run them and actually get the data, right? And then you train a neural network using that data, right? And try to get a neural net as accurate as possible to your ground truth. And the advantage of getting a neural net is when, let's say I come up with a new gen hardware, I really don't need to rewrite a lot of new stuff that has been, added to your new hardware. I can just retrain the new model. I can do something called transfer learning from the old models and apply some retraining techniques to get to the new model very, very fast compared to what you can do to actually build your analytical model. Now, there are obviously detractors to that approach. People may say that with the analytical model, I can get details as to what is really happening. I can get more understanding of things. True. But you may not get to know exactly how neural network is representing each and everything of your microarchitecture inside. But if you're just interested in your prediction accuracy and not into the whys of why your architecture is behaving, then you can definitely replace it with a neural net, because we'll see that it has very, very high accuracy compared to an analytical model or analytical models.
So, question there. So it's a quick question. So the ground truth you said, right? For new architecture, the ground truth we need to get a new ground truth, right? So you are just saying that we need to retrain, we need to capture the ground truth again for the new architecture.
Yes, so it can be simulators, it can be other stuff, and then you can use like a transfer learning. Like basically, you can probably keep, let's say 80-90% of your neural net the same, and then maybe you need to add something or drop something with your new ground truth.
Okay.
Yeah. So The way Ethermal models so what does it do? So Ethermal takes your x86 instruction set, right? And once again, now look at it like, earlier for your deep tune work, we were modeling OpenCL code. Okay. And you're directly taking the C OpenCL tokens and then trying to create an internal representation so that our models will understand. Here, the input is not C, C++, or any other high-level code, or not even LLVM IR. It's actually x86 instructions. It can be, extended to any other assembly instructions for that matter, or even, even your LLVM machine-level IR for that matter. And so this is how they represent it. They represent it using a two-layer LSTM, not a single LSTM. Now, it's a very interesting representation, and I think it would be good for you guys to go and study this two-layer LSTM model, because this can be very useful later when you are trying to represent various IRs. It can be one of the techniques that you can use for encoding or IRs. And what does it do? So one layer of the LSTM is for one instruction only. Okay, so basically, if you see that I have a move instruction followed by, let's say, an add instruction, right? So the move instruction is being encoded using move. This is the space, it's a constant, and then several other things that you use in your move instruction. Similarly for the add instruction. And then you will do a similar token embedding that I showed you earlier. Now, this is a lookup table. It can be learned ahead of time. It can be learned in place. Both of those things can be done. Now, what will happen is after that, each of these tokens of your x86 instruction will have a vector representation. Now, this can be, once again, 100 dimension, 64 dimension, whatever it is, 128. So you can see vmove, vs, vconst, and nothing else but the vector representation of all of these. So this will be unique values. So vadd will always have a unique value, and vebx will always have a unique value, and vecx will always have a unique value. And this is the first layer encoding of the LSTM. So the first LSTM, what it will do is it will take this as input and generate one output. So for the move instruction, you'll get an output, right? For the add instruction, you'll get another output. Similarly, if there are 10 more instructions in your instruction set, you will get, for the first layer of LSTM, you will get output for each of these instructions. So you will actually have, let's say, 10 of them like this. And then you create the second layer of LSTM. You can consider this second layer of LSTM as for the basic block. So this will be for each of these instructions. So you'll have 10 LSTMs here, 10 LSTM cells. Whereas here, you will have as many cells as the number of operands in your maximum number of operands in your x86 code. Okay, so this is the first layer, which is for each instruction of x86 along with its operands. The second one is for your each basic block, which is at a higher level. So mainly you can see one layer of encoding for your instruction, then the second layer of encoding for your basic block. Now this can also be, you can think of, let's say you have an LLVM IR, or you will have LLVM MIR, machine IR, and you can think of, okay, I'll encode each LLVM IR instruction as a first layer LSTM, and then I can encode the entire basic block as a second layer LSTM. Okay, now you can say that, okay, but I do not have one basic block. I have multiple basic blocks connected by a control flow graph. So you may want to actually represent to the third layer LSTM with a control flow graph. Now that may be various other representations of it. I'm just giving you an example. Control flow graphs and how LSTMs occur through control flow graphs can be handled by different mechanisms. There are people who have tried to use something called what are called as graph neural nets. That is, you have your control flow graph where each of your node is similar to something like the second layer of the LSTM. Okay, and then you can use something like a message passing between each of these nodes. Let's not get there, it's slightly more complicated. But let's say you have this two-layer LSTM, and finally you will have is throughput prediction. So if I go back to this slide, what will happen is you will have move, add, shift, let's say, and you have this two-layer LSTM, and finally a prediction will come out. You compare it with your ground truth, that is, what is the actual number when you run it through your hardware, And then you get your error value and feed it back to the back propagation, and finally, after many rounds, it will finally converge to a value as close to the output as possible. Okay. Any question on this mechanism?
So I have a very basic question.
Yeah.
So the problem which this model is trying to address is pretty straightforward, right? Instead of collecting the cycles using the PMU events for a particular base, one can even collect the number of cycles for each instruction and then effectively use it to find the block throughput, right? So exactly where is this model going to give benefit? Because that's a pretty straightforward data. I mean, each instruction already has a set latency on a particular target.
Yeah, because see, these
So
hardwares are all out of order machines, right? So just by
right.
adding the latency values, you will never get the right numbers. Okay. So your model is not as simple as just adding the latency values of your each instruction. It's actually probably an upper bound. Okay. So it will give you an estimate.
Okay.
Definitely you can use it as an estimate, but it is not as close to your actual running hardware. It will just give you an upper bound of your number. Okay.
Yeah, out of order characteristics is not.
Yes, exactly. So mainly to see
yes.
if it's an in-order machine, then probably you don't
Yes.
require so much of fancy stuff.
Even the cache effect.
Yes. So let's say currently,
Captured
this
by a
paper simplifies stuff in the sense that it kind of assumes things are working out of cache. If things are not working out of cache, you can have various run-to-run variations also depending on how your machine is loaded and so many other things. So let's say you are working mostly out of cache. At least that part is that variability is taken care of. But yeah, I mean, if you want to even take cache's account into effect, maybe you have to build a more complex model for it. And so if you look at the results Ithamol derived for a range of mainly Intel hardware, it shows that it almost gets cuts down on accuracy error by close to 10% or more in various cases. And it actually looks very promising. And as I said, that for external people to develop, say for example, like if you are not an Intel hardware engineer or not an AMD hardware engineer, or let's say an ARM hardware engineer or an NVIDIA hardware engineer, many of the details, if you want to do or write simulators, write something, you will always be missing out on stuff because maybe there are specifications you don't know about, maybe you encoded wrongly, and so many other things. So this is a much faster, easier, and I'll say more, tuned to the open source community for people who want to build pretty accurate models pretty quickly. And then once again, as I said, they use two-layer LSTM models, but then there may be various other techniques people can apply for the same piece of x86 instruction. Now, I just showed it throughput for basic block, and if I want to know the throughput for an entire function, as I said, then I have to somehow model the control flow graph. I may need to model the path. I may need to know how things are flowing, and there we have to probably do much more complicated stuff compared to what the authors did here. Okay, going on to the DL-based graph coloring register allocation, this is a work that we did around a couple of years back. Many of you may be familiar because we had presented this in LLVM HPC last year in 2020, and so that I'll go through quickly. I have some more stuff to talk about. So about the graph coloring problem, right? And I'm not going to go deeper through that. It basically means that I need to allocate colors to the nodes of a graph such that there cannot be an edge where the two ends have the same color. And the minimum number of colors that you can use for coloring a graph is called its chromatic number. Okay, so it's a hard problem, and then it's usually solved using heuristics. There is no well-known polynomial time problem to solve this. And if you look at register allocation, though LLVM compiler doesn't actually create this kind of a graph, in general, register allocation being looked as a graph coloring problem came initially from Chaitin in 1982. And since then, a lot of compilers used it. LLVM uses it in a kind of implicit way, but not by creating an explicit graph from it. And what is the graph that we create? It is called the interference graph. And this is nothing else but the interference graph of the live ranges. For example, you have these live ranges for your, various variables. I'll not go into that. You guys are all familiar what live ranges are. And then the graph actually kind of figures out what is, which live ranges intersect. Like, for example, here you can see H is intersecting with all these other live ranges, but not with some of the others. So you create a graph out of these, and then by coloring this graph with the minimum number of colors, you can get an idea of how many minimum registers you need to use. Now, many of these bigger graphs may have, chromatic numbers much higher than the actual number of registers available on your machine, in which case you have to do spilling and splitting and all those other kinds of more complex optimizations. Okay. So here, the problem was viewed in a slightly more simplistic manner. We didn't want to go into the splitting, spilling, and all those kind of open problems. So what we tried to do is, given a graph, so here we don't have an IR or anything like that, or an input like C or assembly. Here the input is your interference graph. And once you have an interference graph, we actually tried to figure out, what is the best coloring number for this, and we wanted to compare it with what LLVM's greedy register allocator was providing. So we really didn't integrate with LLVM, but it could have been done with some effort, though we have not done it yet. So the way we do it is we represent the interference graph using an adjacency matrix, right? Adjacency matrix just provides a value of 1 if you have an interference, and it's 0 if it doesn't have an interference. And then we have now instead of a 2, so don't look at it as a layered LSTM. This is not like as in the ethanol stuff, but this is more like the 2 LSTM model that we saw in the earlier DeepTune work. So this is like 3 LSTMs, one after another, stacked, and each of these LSTM layer takes one of these adjacency vectors as its input, right? So if you have an n cross n matrix, this is of size n, and there's a limit. So currently we work only with a maximum of 100 node interference graphs, and you'll see later that we actually did not take into account interference graphs which are of size higher than 100. Now that's just a small, I'll say drawback of the mechanism. We can definitely increase it to more than that, but there are other challenges which we can talk about later. So once you provide this adjacency matrix to this LSTM, and finally you go through this on a dense layer, and so the output of the LSTM and the dense layer is a color for each of these vertices of the graph. So this is the overall model. So mainly what we do is from the compiler, let's say LLVM or any other compiler, as you enter your register allocation phase, we collect the interference graph, push it through this model, and get a coloring out. So there is no heuristic involved. We are not doing, currently we are not getting into spilling and all that. Just try to figure out, like, if we would have got this from our model versus if we got it through the greedy register allocator, are there any advantages to it? Okay, so we trained this using random graphs. We actually had about 10,000, 12,000 random graphs on which we trained this model. Now, we definitely could have done better by training it on LLVM graphs, but we didn't want to do it specifically because we didn't want to bias the model specifically for LLVM. But if you are specifically building it for LLVM, you can definitely use your LLVM graphs also as a training set for learning. Okay, and then what happens now? There was a question earlier about correctness, right? Which is a very, very important part of it. Now, as you can well understand that in LSTM and other kind of models, except RL, it's difficult to encode constraints. So for example, I cannot encode a constraint that this edge, these 2 nodes cannot have the same color. I cannot encode that constraint very easily. So what we do is, so once you train and you infer, actually you may get coloring which is invalid. Okay, it's a possibility, and we see that when we build the model, we got about about, depending on the graph size and the graphs, 10 to 30% of the edges are invalid edges. Now, what do you mean by invalid? As I said, that invalid edge will mean that both the nodes of that edge, the endpoints of that edge, are the same color. So what do you do in that case? Because we cannot give that as an output because that'll be invalid. So we have a hybrid mechanism. We run the deep learning model, and then we have what is called as a correction phase. So we actually don't need to recolor the whole thing again. We just look at the invalid edges and do some what is called as a greedy or a local correction. This is much faster than actually running the whole graph. And because we have a very small percentage, 10% to 15, 20%, sometimes maybe as high as 30%, it's still much smaller than the number of edges in the graph. We can locally correct them, and then you can have actually corrected graph coloring. Now, how does it compare to a proper coloring? So what we do is we ran it and we saw that we are generally, like in many cases, very close to the optimal coloring, and sometimes 2 to 5 colors more than the optimal coloring on most of the set that we ran. For example, this is a famous forest fire graph. This is not from any LLVM, but a graph which is used in the literature a lot. And it has a chromatic number of 5. That is, the best coloring that you can get is 5. So once we use our LSTM model, we see that it is actually getting colored with 4 colors. It's obviously not possible. And rightly so, we see that there are 2 invalid edges. One invalid edge is the C3, and the other, between node 3 and node 2, and between node 5 and node 1. And this is both are colored with 2, color number 2, both are colored here with color number 3. So what we do, we can reuse the colors. So what we can see is none of the neighbors of node 5 has color 3. So instead of C2, we can change it to color 3. But once we come here, we can see that it has edges to nodes of all kinds of colors. So we really cannot just recolor it using an existing color. So in which case we actually add an additional color. So instead of using C3, we actually now have a new color called C5. And then you can see everything is well and good. And we are now able to color it with 5 colors, which is the chromatic number of the graph, by using the deep learning model and the local correction. Okay? So this is the mechanism that we used. And when you compare it to the deep learning based graph coloring register allocator for the spec CPU 2017, what we see is we actually collect it after the live interval analysis, and we don't go through all these phases, but we collect the actual number of registers used from the x86 generated set, and we compare it to our color register assignment that we do. And we see that in several benchmarks, we're actually doing better on an average compared to the greedy register allocator. And in many cases, we are actually very close or comparable to the greedy register allocator. So you can see that, and this is like without using any heuristic, like in the compiler. Now, how we can embed, a possible way to embed in LLVM is shown in our paper. Have a look. I'll not get into that because after our coloring or register assignment, it is still possible that we may have to go through these phases. So this may be common. So there has been now some new work that people are trying, where they're trying to take our kind of mechanism and try to do the whole thing instead of just doing for before this spill weight and all those things, which will be like the allocation, the actual allocation for the entire thing, even if you require spilling and splitting and things like that. So the code is here. You can have a look. You can run it, and if you can collect your your interference graph from your LLVM code, you can actually compare and see what is happening with it right now. On this?
So I have a question regarding the compile time. So how does this model perform in terms of the compile time compared to the greedy register allocator?
Yeah, so that's a good question. We haven't really done that, but what we figured out that the inference actually runs very fast because we are not handling very huge graphs. What we saw with Spec CP 2007 is most of the graphs are within 100 nodes. That's why we took 100, like let's say 90 to 95%. And there are 5% interference graphs which are above 100. We saw some actually even of the order of, in NAMD, I think we saw about 800 node graph and things like that. So for them, the inference may be slightly slower, but it's not very, we saw that it's like very fast in terms of interference. Like we ran 8,000 graphs or things like that in a second or so, things like that. So I don't think it will be a huge difference in terms of actually deploying it. But it's a good question. I mean, maybe once we deploy, we may need to see whether we may need to run the inference faster and things like that to compare with heuristics that's been there in the GRA. Yeah, and maybe like, we probably cannot put it in JIT or other stuff right now. Maybe only offline compilers. But yeah, that's a good question.
Okay. Another
So
question
how
is, yeah, please.
measured? Is it in terms of the number of spills which it is able to reduce, or?
No, currently, currently that's why the comparison is a bit convoluted because we are not doing these spills and all that stuff. So what we did was we took just from the live interval analysis and figured out, like, let's say, we figured out from a 70 node graph, we require 10 colors, right? And then I take the output after everything, after your actual LLVM generates your x86 code. I see that, okay, it is taking 9 or it is taking 11. Okay, so that's the comparison at this point of time. So if it actually exceeds the number of registers, right? Let's say we have 30 registers or 26 registers available or 32 or whatever. If it exceeds the number of registers, I have to go through this same mechanism. So if I really need to spill, I have to go through a similar mechanism, which is not built into right now. So if you look at it, what we see is we were doing about 2 to 5% better if I just do an LSTM based model, let's say for the ones which don't require to spill.
Right, but it may incorrectly predict the more number of registers, and then it may lead to redundant spills, right? Because that is something which is out of the model. So the model will just predict the number of colors required to.
Yeah. So right now, that's what some people are trying to work through the entire, let's say, the flow. Right now, if you don't require a spill, even now what is happening, let's say you have enough registers, but even then your GRA may be using more registers, right? So we will be using lesser register. Now you may say that, okay, if you're not spilling, how does it matter? Okay, you may actually improve power by using lesser number of registers. So that's probably what will happen. So if you really require a spill, okay, if you really require a spill that, okay, whether you go through LSTM based model or this model, you really require a spill. Right now, at this point of time, we really didn't evaluate it. I think we will probably have a similar number, but it can be a bit different. Let's say, this GRA, let's say, predicts 40 registers. We predict 36. So in that case, our spilling, even if you go through all this, our spilling code will be better. If you now predict more, yes, it will become worse. And there's currently the only thing that we do, we just look at our paper. What we say is, we cannot just use this model right now. It will be a blend of both. We run it both through the inference mechanism and through this mechanism and take the one which is better. Okay, so that's what we had proposed. And in the long run, if you are trained enough, maybe we can replace.
So there are certain instructions which have
which
have hard dependencies on existence of operand on specific registers. So those constraints are also
yeah, those are not handled. Let's say, currently I don't handle things like I require a vector register, right? Or certain things need to be in, certain registers for your stack and all those kind of things. So that's why I take it with a bit of salt. The thing is, the overall viewpoint is with this kind of mechanism, you can get very close or comparable performance to a greedy register allocator. But yes, so if there are hard constraints that are being put that are not being taken care, we can actually take care of it by saying that, okay, remove the variables which require these hard constraints, and then you can apply the same algorithm on the rest of the graph. Okay, So you can actually do it in that mechanism also. But yes, these are all good questions. So because we did not really implement it in the LLVM, so these questions we did avoid at that point of time by just showing that, here is a mechanism which is doing pretty well. But yeah, and once you start to put in practice, there may be some challenges we have to go through.
So DD, just to add, I think SpecInt it really performed well because SpecInt doesn't demand much of a vector register because it's an integer benchmark, right?
Right. Yeah. So we didn't really run at, I think we ran 1 or 2 spec FP, right, Venkat? I don't remember right now.
Yeah, so mostly it's of SpecInt.
Yeah.
Is it possible to encode the constraint, like maybe not use LSTM and like some other model?
Yeah, that's a good question. So just look at our paper. There's a reference to a paper by guys from Baidu. Okay, so the Baidu guys did a reinforcement learning based register allocation. Have a look. The only problem is it's an extremely complicated model, and you'll require a lot of compute. So this we actually ran on some AMD servers and got the training done. But that RL was actually run on a big Baidu NVIDIA supercomputing pod like setup. Because they were looking actually also at much bigger interference graphs and things like that. But yeah, people have tried reinforcement learning. People even have tried something like graph neural nets, which is not LSTM. So have a look at both of them. You can see those alternative models.
I think even in LSTM, like there should be like some intelligent encoding, right? Let's say like do some negative weight for like invalid edges.
Yes,
right?
you can do, but
that
at the same time,
forward.
the problem is it cannot guarantee. I mean, see, the
Yeah,
thing is, it will not guarantee, it will only probably reduce your invalid edges and things like that.
Okay. Makes sense.
But in RL, it is guaranteed because in RL, if you see a clash happening due to an invalid edge, you don't go through that search path. You just block that search path.
DDA, using an RL, does it, if it is trying to guarantee, does it mean that it increases compile time as well?
Yeah, obviously RL will be much more, as I said, RL is much more compute intensive. Okay. So it will definitely take much more time to infer things and all that. But yeah, it depends on your compute setup. If you have, let's say, a supercomputing at the back doing your RL, maybe you will have comparable time. It depends on what kind of compute infrastructure you're able to provide for doing a compilation. Okay, so I'll go to the last part, and actually I'm over time in terms of I need to run somewhere. But anyway, we'll go through this quickly. This is an RL-based stuff, but I'll give a very, very high-level idea because this is actually one of the more complicated papers where they try to do auto-vectorization using what is called as imitation learning. And when I say auto-vectorization, it is not really loop vectorization. All of you, once again, are from the community, so I don't need to spend a lot of time. I had to spend a lot of time with another group trying to explain what is super level parallelism. So this is more like SLP. So we are going to talk about SLP and not loop parallelization. So what happens in this case is, if you know in reinforcement learning, if you are aware, what happens is you have a state, and then you want to expand the state space, and you want to apply a transformation and go to another state, and you want to go to another state which has kind of a more optimal cost in terms of in your traversal tree. And so for example, given this code on the left hand side, let's say one round of transformation will try to vectorize A1 and A2 together and create this particular piece of code, right? That's like one step. And then maybe in the next step, problem is, sorry, I'll just go back. Yeah, the problem is if you do it naively, you may try to expand this step also as a vector packet, but you know that plus and star are not isomorphic and cannot be done. So reinforcement learning, when you are, that's the thing when I'm saying about correctness, you can encode this correctness that when you're trying to expand the step, you can encode that, okay, if I see this kind of non-isomorphic stuff, I do not go to that state anymore or don't expand that state further down. Okay, so RL, you can build this kind of constraints into the RL. Now, in RL, what will happen, as I said, you have to choose a valid action. So as I said, the first one, maybe, I can pack between A1, A2, or A2, A3, or A3, A4. But I'm not showing that you can pack A1, A3, or A1, A4 because they are not adjacent. You can actually do a packing, using some kind of gather mechanism, gather ISA, or you can actually store using a scatter ISA. Let's assume that we are not going to do that. We'll do the vector packetization only for adjacent memory operations. So these are the possible valid actions, and you can choose, let's say A1, A2 is the valid action you take, and then you go to this next state which is valid. And then from this next state, you can choose another valid action, which is like, vectorizing A3, A4, and you go to the next state, which is this. And you can continue, if you have a bigger basic block, you can continue in that direction. And this is like exploring the space, and you probably will try to, if your vector size is higher, you can actually even try to now convert A1, A2, 3, 4, 2 together into one more packet as a next step. Okay, or maybe you could have done it earlier here also. So it depends on what is your vector size, what is the vector factor that your machine allows, and then you basically explore your state space, and then the regular, what is called as the MDP formulation, or M stands for the Markov decision process, and you use this mechanism to build your model. And what the researchers found out is you can actually try to packetize top down or bottom up, and I think they figured out that top down was doing better, at least for this kind of code. Now, the state formulation, I'm not going to the details for for the sake of time, but you can actually read the paper. Each state actually is not just a simple state, but it carries a lot of other information, right? And this is from this paper, How to Modernize Compiler Technology, from someone Singh et al. So you have something called the package, which are the possible packets that you can pack. You have a dependency edge. You have what is called the focus edge, basically which one is the one that you are going to packetize next, and things like that. And then you actually explore this state space. And the way you explore the state space, it's based on an earlier paper. So you have to read two papers. It's based on an earlier paper from the same authors called Go SLP. If you have read that, it's actually a pretty nice paper where they formulate the SLP problem as a constraint satisfaction kind of problem using integer programming. And once you have the constant satisfaction problem, you actually solve it using some of the constant CSP solvers. Okay, so what this work does is it tries to imitate, that's why it's called imitation, it tries to imitate the steps of the constraint satisfaction solver using a graph neural net. So there are so many terms that I'm introducing, so don't get confused. So what happens as a result is, if I want to go from one state to another, what would have this Oracle Go SLP would have done? Which ones would it have combined? So it actually learns. So that is your training or learning. You usually have your basic block, and you use your Oracle Go SLP to solve it. Okay, and once you solve it, you actually use a model, which is a graph neural net, to actually do this valid action by imitating that particular Go SLP action. Okay, so that's how it happens. Now there may be very big basic blocks which the solver cannot solve. As you know, solving constraint satisfaction problem may not be easy, and especially if your basic blocks are big, it can take a long time. So you may need to break down your basic block and solve it and things like that. So these are all like complexities in this. So yeah, so this is a reinforcement learning approach for the SLP vectorization. You will also see a later paper, which will just refer to, not talked about, where they use an RL-based approach for doing inlining for code size reduction from Google called MLGo. And these are some of the new work that is coming up based on reinforcement learning. Now, the good thing about reinforcement learning is Actually, you need not have a lot of training set. You can do a self-supervised learning, right? And in many cases, you will find solutions better than what exists today, because you are not just blocked by your training set and things like that. But once again, be aware, RL is compute intensive, and you need to have very good hardware to run your RL stuff. Luckily, you now have Facebook's AI Gym and things like that, which you can use probably and get pretty good performance. I think some researchers already try to do that and are getting pretty good results. So you need not be that you need to have your own homegrown hardware to run your RL stuff. Then these are some other, these are the related work we have been talking about in this last 1 hour or so. Chris's PAC paper, Ithamal, deep learning hour work, auto vectorization at NeurIPS 2019. And this compiler to this is how to modernize compiler technology, once again from Saman Charit. Sam Larson, who is the original proponent of SLP, Ajay from ex-IIT Hyderabad student, and these guys. So some other work we did not cover. If you want some interesting work, LLVM HPC conference last year had some interesting work from these guys, Mohammadil et al., who tried to do deep reinforcement learning based phase ordering problem solving. Okay. Hajali et al., this is from some Intel guys, ex-Intel guys, I think, sorry, Intel guys, CGO 2020, neurovectorizer. MLGO, this is a much newer work from Marcio Trofin. He's actually also running machine learning kind of monthly meetups over phone. And Compiler Jim from Facebook, this is mainly Chris, after finishing his PhD, has joined Facebook AI, and he's trying to build this Compiler Jim, which will kind of help you with doing RL research over the cloud and using Facebook's infrastructure. So you may want to have a look at that. So wrapping it all up, as I said, we are just at the cusp of utilizing these techniques. These are pretty powerful techniques, but there's a lot of work to be done in this area. I mean, it's people are still like scratching the surface to figure out what are the challenges, how best to implement these things, how to represent your inputs. There may not be a consensus on everything, because as you can see, the machine learning community itself is evolving, and they are generating newer and newer techniques every day. So conclusion and future direction, my personal opinion is RL is too costly to be introduced for all optimized phases. Now, you can introduce it for some phases, and as someone was asking, it may blow up compile time, and you may need sophisticated hardware resources. And my personal opinion is future optimizations may be a mix of NLP-like techniques and RL models. So some of them which may be RL, and some of them is more like NLP. And some of the open questions which I have great interest in is like, can you use more hybrid models, like where we have part of the code transformed or analyzed using a DL model, and then you have a normal program, which is a very greedy, fast program, which can correct it even if the DL model is not totally correct. Okay, so this may be much easier to do, or much less compute intensive, and get results very close to your RL models without using so many compute resources. And then can these models be really portable across compilers and across hardware? So this is a new paper, a very new paper from, once again, Chris Cummins and Hugh Leather, his advisor. Have a look at it. It's pretty nice. Machine learning compilers, past, present, and future, where they talk about the new compiler as a service, optimization as a service, right? And that optimization as a service is currently kind of based on RL, but it may not necessarily be RL. So, we started with this slide. Let us end with this slide. So, for many of us who are deeply involved with compilers, are passionate about optimizations, maybe there'll be a future where instead of analysis and optimization, we'll have a learned analysis, and we have a learned transformation. And we may, as we do more and more, maybe this bracket will expand, and maybe sometime down the next 5 or 10 years, we'll see quite a bit of optimizations using learned analysis and transformations rather than handwritten heuristics. So yeah, that's all. I think I overshot my time quite a bit. Thanks for listening in and asking questions. I can take a few questions now.
So we need a name for your tool as well. Like other tools have names, right? Like Ithmal and DeepTune.
It's called DL for Edge or something. I don't know. Yeah, so
It will
we
be
are also
like
building new stuff.
DDTL.
As I said, we have built some new stuff for doing people.
Okay.
So we are calling it Neural Instruction Combiner. So you'll see some parts of it in an upcoming talk. So
Nice. Okay. Yeah, well, it was a lot of information, but the thing is, it was personally for me, I learned quite a bit, getting a higher level overview of what is going on. Sometimes we get too deep into what we are doing and like miss out on like what is out there. So I thank you so much for taking your time and spending with us. Where is
okay, thanks to all of you for attending on a Saturday evening and asking questions. Hopefully it's of use to you. I can share the slides if you are interested, so that you can have a look at some of the references. As I said, it's an upcoming area, so you may need to read a lot and figure out things, write some code yourself to understand. But some basic stuff can actually be written pretty fast, frankly speaking. The encoding and other stuff, you have so much of support now in TensorFlow or PyTorch and all those things that you probably can write it in a week and then already get going on some of these things.
Yeah, okay. Yeah, Pradeep will post the slide deck on the meetup. And
Okay.
Yeah, I will
can
also post
share
the
it.
recording.
Okay.
Okay. Anything else? Okay then.
Yeah, if there are no further questions, yeah, we can end the meetup here. Thanks for being with us. It was very interesting talk. Yeah, we're looking forward to more works in this area.
Okay, yeah, thank you very much. And I'll suggest that you folks also start looking into this, because yeah, more people looking into it will make some of these things move faster, because we have done heuristics for a long time.
Yeah, thank you.
Okay, thank you a lot, and bye. Good evening.
Thanks, BNU. Bye.